Hi everybody. You're hopping onto this video because you were interested at where this weird number came up that we use the symbol E to represent. So for us to go through and just address like Euler's number and if it piqued your interest again to want to know where that came from, then I think that that's great. What I want to do is I want to kind of walk through two different ways that we could kind of talk about where the number came from and what it represents. Like, what is this 2.7182 blah, 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 blah number really getting at? So what we're going to do is we're going to look at two different approaches. Okay, so what we're going to do is we're just going to walk through this chart. And I want to just maybe explain some of the simplification that's happened in the chart, just so that you don't think that I'm fudging anything on you. Really what we're going to do is we're going to look at the effect of changing our compounding period. So I want you to notice that we start off compounding yearly, and we're going to keep working our way down. And I'm just going to slide this up on the screen so that we can see we're going to get down to compounding every second. Okay, so what we're going to look at is the effect of having these different compounding periods. Now, as we work our way through that, we're going to look at some specifics in terms of our calculations. Again, I don't want you to think I'm fudging anything on you. We're just simplifying the numbers because the numbers really don't matter. The first thing I want you to notice is that we're calculating some compound interest, the effect of compounding. So really what we're working on in this middle column is our relationship for compound interest. I just want you to notice that in the problem, what we're going to look at is taking a $1 investment. So really what that translates into then, if we want to look at it that way, is that our p-value is 1. And therefore, really all we have to look at then is our growth. So if you just quickly scan down the middle column then, you'll notice what we have is just the power portion of our compound interest formula. Okay, hopefully we're good with that. Now I want to break down some of the components to it. The next thing we're going to do is we're just going to look at 100% interest. So we're going to look at the idea that one thing doubles. And then we're just going to talk about, well, how long does it take to double? So if I see then that I've got this 100% interest, then that's why the top of all my fractions are 1. 1 being the decimal number for 100%. Okay, the next part I want you to focus in on is our compounding period. So one of the things then that I want to address, and I'll just get rid of that highlight on the 1, is that this yearly, in the first one, is why I am dividing my number by 1. Semi-annually, why I'm dividing my interest by 2, quarterly by 4, so on and so on and so on. Okay, we should have that given our previous discussion on compound interest. But the second part then, because it's yearly, we're going to have 1 compound per year. Because it's semi-annually, we'll have 2 compounds. Because it's quarterly, we'll have 4, and so on and so on. So what we're going to look at then is the effect of just taking 100% of something, doubling something, but examining what happens if we increase the number of compounds per year. Okay, so let's take a look at the first one. We can go through and we can calculate that pretty quickly. You have your 1 over 1, which is 1. 1 plus 1 is 2. 2 to the exponent 1, 2. Now, just stop for a second and realize that that should make sense. If we start with $1 and it's going to receive 100% interest per year, then how much money would you have at the end of that year? You'd have $2. The $1 of the original plus the extra dollar in interest. There's your $2. Okay, just to make sure, knock off the next two calculations, the ones with the highlights. Okay, pause the video now, calculate those. Okay, we should be back. So if we take our 1/2 and add it to 1, and then we put that to the exponent 2, we should come up with 2.25. So $1 would grow to $2.25. We take the next one, and we should have got approximately 2.44. Okay, we should have had a little confirmation. Now what I want to do is I want us to go through and fill in the rest of the chart. So let's do the next one together, and we'll see how far we can get. For monthly, that means that I'm going to take my 100% interest, compound it 12 times per year, but now I'm going to have 12 compounds. So we can do our 1 divided by 12, then add on your 1, hit equals, then put that to the exponent of 12, and we should come in on approximately 2.613. Okay, so if we just start to now continue that process, I think we should be good. I think the only thing that would actually hold us back is whether we remember like how many weeks are in a year and so on and so on. So let's go ahead. Let's try to fill in the rest. I want you to pause it now. Okay, and we're back. So I am hoping that we would have said we know that there are approximately 52 weeks in a year. Multiply that by 52. And so we should be okay in that context. Now when we go through, and yes, we're going to push some buttons, 1 divided by 52, add on your 1, put that to an exponent of 52, then we're going to get approximately 2.693. Okay, our next one, daily. Well, we have 365 days in a year, approximately. And so if we calculate that, then we'll get approximately 2.715. If we then took our number of days in a year and we multiplied that by 24 to get our hourly, 24 hours per day, then we find out that there is approximately 8,760 hours in a year. We calculate that, and we're going to now get 2.7181, and so on. And I think some of us are seeing where this pattern is going. If we now multiply that by 60, because there are 60 minutes in each hour, then we're going to start to get like really huge numbers. 525,600. But we're also now going to compound that 525,600 times. And when we get that, we're going to get like approximately 2.71828, and that's still going. And then we get down to yikes. Okay, and this one's going to be even tough to fill in on the page. I'm going to try to do the denominator first. If I take my 525,600 and multiply that by 60, then I'm going to get 31,536,000 seconds. And yes, I'm going to have a tough time fitting that in. Yikes. And when we get that, we're going to get approximately 2.71827. And so on. Now, there's a couple things that I just want to address on this page. This is going to give you a very good understanding for what E represents, like what it represents. But we also need to kind of address that, like, we've been given what an approximate value for E is, and it almost looks like the chart is like walking away from it. Okay, I want to address maybe one big thing. I would hope that back up in here, when we talked about how many days there were in a year, that there might have even been like a little hesitation. Like, it's often come off as kind of that little smart-ass kind of comment of, but is that like a leap year? Well, I hope we understand why we have a leap year in our calendar. that the number of days that it takes for the Earth to circle the sun is not exactly 365. It's like 365 and a quarter. And so every 4 years, we add on an extra day so that for us, we don't start to have snow in June. That actually, if we were to kind of nail it out, like there's 365, like 0.2425 days in a year. And so I hope you can just see that we could kind of adjust all of those figures down with that actual or a more accurate value. Okay, so we can still see that we're approaching this 2.71828, blah, 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 blah. Okay, what was the whole point of that? Why is that coming up? Well, I want you to take a look at what's happening in what I highlighted down at the bottom. That really what we're looking at is we're looking at how something is growing. But rather than like artificially growing, you know, I will pay out your interest twice a year. I will pay it out 12 times a year. Like now, when we get to the every second, it's almost continuous. And I want you to think about growth. I want you to think about growth. That if we came back up and we examined our quarterly, and we moved away from money, and we started to think about like people, about living things. Living things grow throughout a year. They don't hold steady, and then 3 months in, we grow. We hold steady. 3 months have passed. We grow again. Now we hold steady. 3 months pass. We grow. Now we hold steady. 3 months pass. We grow. That's the way your formula treats compound interest. It says during all of those arrows, there is no growth that occurred. None. Until the very end. Then there is no growth that occurs until the very end. Well, the problem is growth is always occurring. Like cells are doubling. We are growing. And so that model of quarterly doesn't really examine how things grow. That we only actually get closer to how things grow if we make our growth as close to continuous as possible. And so I would even argue that like we get down to the every second and, well, that isn't continuous because you have parts of a second. So do you start to get to like nanoseconds? What does it mean? So for us, if we can start to look at E, as a reference point for continuous growth. Really, all that's your 2.71828 is your growth factor for living things. Okay, hopefully we're able to see that E just represents continuous growth. That's the shortcut answer to it. And we can see why that occurs. Okay, I want to take a slightly different approach. Well, not slightly different, significantly different. What we're going to do is we're going to move away from this idea of just calculating and trying to continuously compound. And instead, I want to look at some stuff graphically. Okay, so what you see on your screen is Desmos then. And what we're going to do, I'm just going to shrink it down a little bit to make sure that we can see the whole thing, is we're going to hop on and we're going to play around with some graphs. So what I want to do is I actually want to go through and punch in a function that we should all be good with, something that's like exponential. So there's my y equals 2 to the exponent x. And what I want to do is I want to examine the slope of this curve. Now, I know that we're always used to talking about slope, in particular with lines. And I know that we've had a discussion in years past about the fact that a slope is changing when we're on a curve. But what we're going to do is we're going to examine the slope of that curve, which means we're going to use a little calculus. Now, we're going to let Desmos do the work for us. But what we want to do is we want to kind of address some rate of change, some slope. And that's all calculus is the study of rates of change. So, before I think we can jump into our exponential graph, we're going to go back to grade 9 a little bit. I'm going to work through this pretty quickly. So, pause it if you need to, rewind if you need to, but I'm going to try to push the pace on this a little bit, at least as fast as Desmos will allow me. So, if I go back and I address maybe a simpler function, a grade 9 function, y equals 2x plus 1. And I was to ask you, well, what's the slope of that line? You should be able to identify that's a slope of 2. Okay, what I'm going to do is I'm going to have Desmos do some calculus for me. It's going to calculate the slope. So what I can do then is I can enter in my function, but I need to bring up a special function. So I'm going to select the function tool on the right. You'll see that I've got some trig functions that pop up. Hey, there's your trig stuff. If I go over to miscellaneous, I can select d by dx. This should look familiar to a bunch of people because maybe in science class, when we talked about slope, you might have really had like a delta y over delta x as the form or the expression that was used for slope. Like that's the same thing as our rise over our run. There's the change in y over the change in x. That's what that d by dx means. The problem is I haven't fit in a function for it, so now I'm going to slide in a function. So I want it to calculate the slope of the function above, so I'm going to enter in the same expression as that function. What you see on the screen now is a horizontal line at blue. So the red was our original function, y equals 2x plus 1. I asked you what the slope of that line was. You hopefully told me 2, and you can see y equals 2 is the slope. Now, you might be saying, why do I get a line for that? Like, why isn't it just a value, 2? Remember that what that slope function is what is the slope of the red line at a given x value. So if I was just to highlight a couple things, and I was to ask you, hey, at an x value of 3, out here, what's the slope of the red line? And you would tell me it's 2. So we have a point at 2. If I was to ask you, hey, at an x value of negative 1, what's the slope? You should tell me 2. Well, at an x value of 1,000,000, what's the slope? 2. At an x value of negative 1,000,000, what's the slope? 2. Hey, what's the slope? It's always 2 for every x value, and that's why we have a line. Okay, hopefully that makes sense in terms of process for why we get another function, another line out of that. Now what I want to do is I want to go through and graduate to grade 10. So what I mean when I say that is all we're going to do is we're going to create some uglier functions. So if I backtrack on that, and instead let's change that to an x squared. Well, now I need the slope of my x squared function. There we go. And there is our function. So again, the red is the original function, the blue is the slope. Now, that shouldn't surprise us that we get a red, and we should be able to the blue graph, and we should be able to reason it out. Let's just take a look at positive and negative slopes, for instance. Like we know that a positive slope rises to the right. It just might take like this form or this form, but positive slopes are rising to the right. And so if I was to highlight where on my parabola is my slope positive, well, everywhere here my slope is positive. And notice that my slope is positive because my blue line all has positive values. Notice they're all positive values. Well, let's take a look, and if I was to ask you, where in my parabola is my slope negative? Well, we should be good. that everywhere over here, my graph is falling to the right. So I have a negative slope. Then that shouldn't surprise us that for all of those x values, your slope function is negative. So at the very least, we get that. When do we have positives? When do we have negatives? Well, the other part that we need to examine then is, but I also have different slope values. So it's not a horizontal line anymore. And I'm just going to get rid of all of that highlighting. Well, if we also took a look at, well, what was the size of the slope? So if we just looked at the highlighted portion right up here in my original curve, and I actually don't want that in blue, I'm going to put that in purple. I'm hoping that we can recognize that as that parabola extends on forever to the right, it's going to continue to get steeper. Like the graph is going to get steeper. And hopefully we remember that steeper slopes have bigger numbers. So that's why way out here, I have a pretty big slope value. But if we were to examine way down here by the vertex, notice that my parabola isn't that steep. And so its slope would be represented by a smaller value, still positive, but smaller. Well, that's why my slope has a small positive value here. And maybe we can see the opposite for all the negative slopes on the other side. But I just want to draw your attention to the slope of my parabola was a line. So the slope function of a quadratic became a linear. Okay, let's jump in and let's just go a little quicker and make the function even uglier. Okay, what if we went exponent 3 and we jumped into a cubic? Well, now there's the slope function of my cubic. I don't think that we need to address in the same detail what we just went through. You can use that same reasoning to argue out. But I hope that we can see that the slope on my cubic is always positive. I am always rising to the right, just at different values. And so notice that its slope, the blue function, was always positive. Except for at the point where we hit 0. Okay, but look at the other pattern. My slope function for a cubic became quadratic. Okay, maybe we can see a pattern, and if I just went one more, and we went a quartic, and now I think we can really see a pattern. That my slope function for a quartic was a cubic. Notice that in all of those cases, when I found my slope function, I got a different function. Okay, what I want to do is I want to jump back now to the original function that we went to graph. So how about we graph 2 to the exponent x? Oops. And I just need my x dot. There we go. Now what we're going to do is we're going to calculate the slope of that same function. And notice something weird happened. The slope of my exponential was still an exponential. Okay, if I take a look on my grid, I'll notice that my red curve was above my blue curve. So for any x value, my red curve is above my blue curve. So now what I want to do is I just want to see, like, is this true for all exponentials? So let me just try another one. Up in my original function, we're going to calculate or include the graph 3 to the exponent x. There's my exponential. We should have been expecting an exponential. Ooh, now I take a look. Those curves are almost the same. They're almost identical. Now, if I zoom in a little bit, I notice that they're not the same, that actually my blue graph is above my red one. Okay, two important concepts. Number one, it looks like the slope function of an exponential is also an exponential. That's interesting. I got the same type of function. Last time with my polynomial functions, I was getting different functions. This one, I got the same type of function. Second part, what's really important is I noticed that my slope function is on the other side this time. So when I had my 2 to the exponent x function, then I ended up with my curve, original, its slope underneath. But now when you take a look at 3 to the exponent x on Desmos, you notice the blue and the red curves, they like switch spots. So it almost begs the question. If it's like the blue curve moved to the other side, is there ever a point where maybe the blue curve lies directly on top of the red curve? Okay, let's play around with that a little bit. So what we're going to do then is we're going to change our base. If that 3 jumped it to the other side, then let's try to pick something that's between 2 and 3. So how about like 2.5? Now that means I need the slope. Ooh, my blue jumped to the other side again. So that means 2.5 is a little bit too low. Okay, let's see if we can go a little bit in between. Let's go right in the middle. 2.75 and 2.7. Ooh, those are almost on top of each other. However, if I zoom in, I notice my blue went to the other side. My blue's above. Okay, so 2.75 is too big. So now what I need is let's pick something a little bit smaller. How about we go like 2.5? And I'll just keep going in the middle. So if I make that my 2.5, there we go. Oh, my blue jumped to the other side, so it's too big. So maybe I just go straight 2. Okay, those are like really close to each other. So I'm going to zoom in. I notice my blue is on top again, so I need something a little bit smaller, and maybe some of you guys are able to see where we go. Like if I put in like a 1/8, and now take the slope, like look how close we are. That if I even then went like now we're even closer. So if I zoomed in, just to be able to see that they're different, can I just get you to look at your scale on your y-axis? Like if you just look at your scale, to be able to tell the difference between those two curves, I am 1/10,000th of a unit apart. Not even per grid line. Because now I got to break that up into 1, 2, 3, 4, 5 grid. I am 1/50,000th of a unit apart. So what I'm hoping then is that for us to be able to take a look at that, we can maybe just see that what that base power is starts to lead us to having the same slope as our original function. There's something pretty important to that. I want you to imagine then, if we change slope to rate of change, that the rate of change of my function is the same as the population of my function. That's a huge concept for us. What that means is my population is changing for all my population. We start to come in on that idea again of continuous growth. When we look at a population of people, that population is always changing. Now, we might argue that like a town could still have 1,000 people in it, and tomorrow it still has 1,000 people in it, but those 1,000 people aren't exactly the same. The town is changing. And so hopefully when we take a look at this, we just get a graphical sense of how E becomes a really important value for us. The slope of E is E. That's huge. Okay, hopefully you just have kind of two different ideas that can kind of give you the idea of this continuous growth, this concept of E. As mentioned in the lesson, hey, for us in this course, if you just remember that E is like 2 point something, then you've got everything you need. Okay, I love the fact you had some curiosity pop in and try to get a deeper understanding of E. That's great. Okay, good luck with your practice.